In this video, we're going to describe how to construct the table which forms the basis for the chart we've been using throughout the last video and before. All right, that table is constructed in the first tab of the Excel file graphical solution right here. Okay, so we're going to start with column B right here, starting with cell right here, which essentially creates a production range for drug 1 going from 0 to 3 pounds in increments of tenth of a pound. Scroll down, you'll see that easily. Producing more than 3 pounds of drug 1 is not possible because it takes 4 hours to produce 1 pound times 3 pounds is 12, the total number of hours available. Okay, now instead of constructing the vertical axis the same way, we're going to calculate it based on the interplay between the production levels of these two drugs we intuitively described before. So next, for each level of drug 1 production in column B, okay, we're going to calculate how much of drug 2 can we produce by exhausting all the labor in column C and then all the material in column D. In other words, for labor, we set up the equation that I've shown on the slide here. For labor, we set up the equation 4x1 plus 3x2 equals to 12, substituting different values of x1 going from 0 to 3 pounds in increments of tenth of a pound, and solve for x2. The solution equation is shown right here. x2 equals 4 minus 4/3 x1, which looks a lot like y equals mx plus b, right, or b plus mx that you saw before, where the m slope in this case is the negative 4/3, meaning that the line goes down, as you know from looking at the blue line here. Okay, the intercept b is 4, okay, shown on the slide as well right up here. Okay, and the blue, and the blue line crosses x1 at that vertex 3, 0, which is also easy to tell. So that's completely describing that particular line, right? So going back to Excel, right here, the Excel formula shown in this cell is just 4 minus 4/3 times x. Right? Please check it out. It's really easy to discriminate. 12 divided by 3 is 4, and 4 divided by 3, that's the 4/3, and then b12, b13, b14, that's the different values of x1. Similarly, in column D, okay, we have the setup for the material equation, which is x1 plus 2x2 equal to 6, and we solve it for x2 and get the equation that says x2 equals 3 minus 1/2 of x2, shown on the slide right here. Okay, so this equation, all right, is the red line on the chart. Okay, it starts at the b, or intercept is 3, as shown here, and the slope is much shallower compared to the labor, so that's why it goes like this and crosses it at the point we know to be the optimal solution. Okay, so this equation is set up in column D, specifically starting here, the same way that it was for column C. You'll notice 6 divided by 2 is 3, okay, and then 1/2, 1 divided by 2 times, again, b12, which is different levels of x in increments of tenth of a pound. Okay, now, the smallest of these two constraints we know is the feasible x2 production. We know that just by looking at this chart, right? The smaller of material and labor on this side is material, and the smaller of material and labor on this side of this optimal vertex is the labor. Okay, and that in Excel is implemented in column E, with the main function. Okay, next. The next step is to use the profit equation for each combination of x1 and x2 in column F. Okay, so column F is going to use each combination of x1 and x2, columns B and C, okay, multiplied by the appropriate marginal profits, right? So 2 is over here multiplying the x1, and 3 is over here multiplying x2 in column E. Okay, so that will result in a sort of a profit column, if you will, profit column for each combination of X1 and X2. Now, when you follow the profit levels in that column, going from the top, right? That's the familiar 0, 3, the top left vertex with a profit of 9. We've talked about it in a previous video. You'll see how the profit increases, right, as we sort of slide down the material constraint towards the vertex, the optimal vertex, right? Increases, 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 and then it's the highest at the optimal vertex, 1.2, 2.4, and the profit is $9.60. Then it switches from sliding down material axis to sliding down the labor, right? And the profit now starts going down even more sharply so, okay, all the way to the bottom, vertex over here where it's the mere $6 for that particular point. Okay, so we've already kind of discussed all this before, but it bears repeating once more. We want to talk about the suboptimal profit levels that are given by using the production schedule that yields a profit that is lower than $9.60 in this example. So the example on this slide uses the point or production schedule x1 equals to 1 and x2 equals to 2 that I've already used before, and yields a profit of $8 that we've seen before as well, which is clearly suboptimal because 8 is less than 9.6. The only additional thing here is that I wanted to visually depict the entire suboptimal profit contour dashed line towards the bottom of the chart by setting the profit level at 8, just like here, okay, and then solving for x2, just like here, for every value of x1, again going from 0 to 3 pounds, an increment of 10 to a pound. So this equation shown right here is implemented in column G, specifically right here. So this 8 divided by C43, right? 8/3 minus 2/3, right? So the 2/3 of 0.67 is the slope of this times again B12, which is the different level of X as you copy it down. Okay, and then this column G produces this bottom contour over here, bottom profit contour over here. Okay. Next, all right, we flip to the other side of the coin, so to speak, right? And ask ourselves, repeat the whole analysis and ask ourselves, what's going to happen if the production is unattainable or infeasible, like x1 equals to 1 and x2 equals to 3 for, pounds of first and second drag produced. Both labor and material constraints are violated by 1 hour and 1 pound, which you can easily find by substituting those numbers right here, 1 and 3, right? Violation by 1 hour and 1 pound. Okay, but the profit, the unattainable one, I might add, of $11 is calculated by multiplying 2 by 1 plus 3 plus 3 is 11, right? And then we want to set the profit equation to 11 and solve for x2. Okay, we're going to get, again, notice the same slope, negative 2/3, right? Negative 0.67. So that means that this line right here is going to be parallel to this line over here. The only difference is that the intercept is not 8/3 but rather 11/3, so it's higher, right? Because the profit level is high. That literally corresponds to taking this dashed line, okay, the suboptimal profit level, profit contour, and shifting it up to here. Okay, that's the 11/3, that's the 8/3, and shifting it, by that I mean in parallel. Okay. So this will, as it says here, produce the upward dashed unattainable profit line. Finally, okay, the optimal profit level is found in the intersection of labor and material constraints, which we've already done. Solving those two equations will give us the x1 of 1.2 and x2 of 2.4. And this is where the optimal profit level is achieved, as this slide is discussing, right? So the optimal production of x1 equals 1.2 pounds and x2 equals 2.4 pounds of drug 1 and drug 2 respectively is going to produce a total profit of $9.60 we are familiar with. That objective function total profit as a maximum in this value, that's the key piece. okay, given the current material and labor constraints. And to see that visually, okay, again, you set up the equation, profit equation now in this case equal to 9.6, and it's your 9.6 contour, which is implemented in this last column using exactly the same equation as before. So check those out, and we'll produce the solid black line here, all right, by shifting from the bottom dash line and going up, or if you want to think of it this way, from the top dash line going down. Okay, either way, you can sort of tell visually that by moving either this way, which is generally the way it goes, or going down from the top, that the point where you're going to touch, enter from the top or exit from the bottom, the feasible region bounded by this red line and this blue line is this corner here, and that's where the profit is the highest, okay, and of course attainable, right? So that's the key piece here that is discussed on this slide, right? And that's why the production of 1.2 pounds for drug 1 and 2.4 for drug 2 is the optimal production or the optimal solution. Okay, so this is a good place to pause.